Now this tutorial question, you read through the PowerPoint slides. Okay, you read through my PowerPoint slides. The steps is there. You read through, study. If a question, come back to me. And the momentum integral boundary layer equation for flat plate, where it explain how you derive the equation for the boundary layer. Okay, so this one also you read through my PowerPoint slides. At the end, you get one equation that you see on the screen here. The momentum integral equation for boundary layer flow over a flat plate, you can define using this equation. The wall shear stress equal to rho v square d momentum thickness. This is momentum thickness over dx. Okay, you read through the PowerPoint slides. The step is very clear on how we arrive at this one. Okay. Then there's a tutorial question for you to practice the application of the equation. There are two tutorial questions for you to practice. Read through the PowerPoint slides, and there's some chart if you want to do problem regarding momentum integral boundary layer equation for flat plate. These are the graph that important when you want to calculate the momentum integral boundary layer equation for flat plate. Okay. Then another drag, we call it friction drag. Okay. Now friction drag, it is because of the shear stress that stick to the surface. Okay, stick to the surface. Let's say you have an airfoil. The friction drag is more on the surface here. Okay, more on the surface here. So the equation to calculate the friction drag is half rho v square BLCD. So basically it's the same as the equation of drag. It's half rho v square or u square A and CD. So if you want to calculate the friction drag, you change the CD to friction drag coefficient, and the A here is the area of the shear stress acting on. Okay, this one. So basically you find by calculating the area. This is the area of the wing. So you take the, maybe this one, you take the L times the B. L times B, you get area. Okay, this is area. Okay. Then there's an example tutorial question on application of this equation. You can read through the PowerPoint slides. Another one is drag. We call it pressure drag. Pressure drag is due to the pressure. So given or another, if you study aerodynamics, this pressure drag fall under form drag. Another name for pressure drag, we call it form drag, because pressure drag is dependent on the shape of the object. Okay, just now the friction drag, this one, the friction drag is due to shear stress. However, when it comes to pressure drag, it is pressure and pressure link up with the shape. So it's also called form drag. Okay. And there's a derivation step to get the pressure drag. So again, what is drag again? Drag, you look at X and Y axis. And if the velocity is along x-axis, and you want to derive the force in lift and drag, so if the force is parallel to the velocity, it becomes drag. If the force is perpendicular to the velocity, it becomes lift. So in this case, you are given a diagram for derivation. You can see that you have an error, and pressure always 90° to the area, right? Always act on the area pressure. So we always convert pressure into forces. So how you convert into forces? You take pressure times the area. Okay, this is a very small area, so PdA you get force, pressure force. And this pressure force is come with the angle. Okay, come with the angle theta. So you break these forces into x and y. Again, okay, you break this into vector form. You can break into two components. So you look at the velocity direction. This one become drag, and this one will become lift. Okay, so in this case, we were interested in drag. So this component is P dA. This is force, right? Force times the angle here. This is when you expand to this direction is cos theta. So when you want to get the overall surface pressure drag, you integrate from some point to another point. So here the pressure drag equal to integration of P cos theta dA. Okay. So from here, after that, you're able to derive by, after you get the pressure drag, you can rewrite the equation by putting the CdP on the left-hand side and the rest of equation you put in this one. So basically, you still back to the fundamental equation, drag equal to half rho V square A CD. So this one, if you want to find pressure drag, this one become pressure drag. CD, this one become pressure CD. CDP means pressure coefficient, drag coefficient under pressure category. Okay. And you can look at the derivation in my slides. Okay. All right. Now, some to highlight is that the drag coefficient can influence by all these factor. Drag coefficient, it can influence by the shape, it can influence by Reynolds number, it can influence by compressibility, it can influence by the surface roughness, it can influence by front number, and it can influence by composite drag. So I'm going to go very fast. I'm going to give you some example on one of these 6 factor here. Maybe I'll go through two or three example. Okay. All right. Now the first one at the shape dependence, the first factor, you look at the graph here, CD over L over D. Do you know how to read this graph? And we have an object of an ellipse object with the L and D. So what happens if we increase the L and D? What I mean by L and D? So what does this number mean? Okay, what does this number mean? What mean by 1? Okay, what mean by 1? Mean your L over D is 1. So if you look at this object, L over D equal to 1 means it's a sphere. It's a sphere object. Means your L equal to D. So you have an ellipse or you have a square, circle or sphere, a complete sphere. What mean by this one? What mean by 6? L over D is 6. So let's say your D doesn't change. So it means that you have a lengthy, this is 6. This is 1. This is D. Let's say your D is 1. Okay, let's say D is 1. So you have 6L here. Okay, so let's say this is 1, 1. Okay, you maintain your D and then you move along this axis. So what happens if you have a longer object? You see what happened to your CD. So let's observe the numbers. So this solid line here, this solid line gives you equation of CD. So CD, you can see that the line is dropping. The line is dropping as you have a longer object. as you change the form of the object. Okay, the CD drop. Okay, and you have another one. Another one is CD equal to D divided by half V squared BL. This is a flat object. Okay, it's a flat object. So you can see that this is a flat plate parallel to the flow. This dash one means you have a flat object. If you have a circle object with a diameter, then you use a solid line. Okay, I already told you that I'm interested in the round object, so make sure you know how to use this diagram. Okay, don't use the wrong line. One is for flat plate. One is for object with a D. Okay, means round object. Sorry, not round object. It should be sorry. The keyword here is one is normal, one is parallel. Normal and parallel, what does it mean? It means that if this is your flow, this solid line here, this solid line is normal to the flow, means your plate is normal to the flow, 90 degree. So another line here is this dash line here. Dash line here is parallel. It means you have a plate here which is parallel to the flow. Then you follow this dash line. Okay. Yeah. I apologize for the earlier explanation. This is normal and parallel to the flow for the flat plate. Okay. All right. Then the rest you can read from my slides. Another shape dependent, as you can see on the screen here, you have different shape and the CD is different. So if you have a more aerodynamic shape, then you have a lower CD, and you have a square body that resists the flow, then you have small CD value. Okay. That's why you see nowadays the car is getting more and more round, more and more aerodynamic shape. Okay. So another one is the Reynolds number dependent. So as you can see from the diagram on your screen here, it's a table that gives you some idea what happened to the Reynolds number or the CD value. So you can calculate CD value if you have a Reynolds number less than 1. Okay, Reynolds number less than 1. You can use this this equation to calculate the CD for circular disc either in normal or parallel. So if the circular is normal to the 90 degree to the flow here, you can use 20. If it's parallel to the flow, then you can use 13. So you can make some comparison what happened to the drag coefficient if you remain the same Reynolds number, you remain the same velocity, but you rotate the orientation of the object, it will affect the drag coefficient. Okay. So you see the round object over here, also same. Okay. One is a full square, one is hemisphere. The Reynolds number will also, the CD will also different equation you can use. Okay, hemisphere you use this one, sphere you use this one. Another one is yeah, this is very interesting graph. So if you see CD versus Reynolds number, and this one is smooth sphere, cylinder. This is my favorite graph. So yeah. So you have Reynolds number, you have CD. By calculating the Reynolds number, you know the value of CD, that you can use to calculate the drag on the object. Okay. So this is how you draw separation with no separation case on a round object. So on the left is no separation. This phenomena we've seen in the earlier session. When we have separation, then we can draw our streamline with rotation, circulation at the back of the object. And this one is a common vortex streak wake, where you will see in the ANSYS simulation, if you're simulating a flow around a body, you will see there's a circulation of flow, and this behavior, we call it karma vortex, right? And so on. So these are two videos that you can see if you're interested in seeing how people analyze the flow along the round body and cylinder. So later you can click inside these two links here to see the video if you're interested. This is more on the CD versus Reynolds number with different shape. As you can see here, if you have a flat plate with the parallel to the not parallel, normal to the flow, you will see is very, very high. And as you change the shape, the line will drop, right? The smallest one is the flat plate that go parallel to the wind, go below flow. So this also a very important chart. Let's look at one tutorial question. So if you read through the question, a worker spray paint to the ceiling of the room. Numerous small paint aerosol were dispensed into the air. Means somebody spray the paint to the ceiling, and you have aerosol bubble suspend in the air. Okay. So eventually this particle will settle and fall to the floor. So this one particles will drop to the floor after a few minutes. Consider a small hemispherical paint, particle diameter given, or 10 micrometer. Specific gravity is 1.2. Specific weight water is given. Dynamic viscosity, this one is dynamic viscosity of air is given. Density of air is given. So you need to determine the time that takes the particle to fall 8 feet. I think this one is, I forget to change. This one should be 8 meters from near the ceiling to the floor, right? Assume the air within the room is motionless, right? Now, okay, let's see how we solve this kind of question. So again, particles is a round object, which is also my favorite question, right? So step 1, identify keyword. So, and then identify the relevant equation. So how we solve? First, you draw the particle of the paint, because in the question, we assume that the paint is small spherical paint. So you can draw a diagram and then draw free body diagram. Free body diagram means a diagram with a force. So all the mass, all the object with the mass will come with gravity. With gravity, you have weight. So you have weight pointing down. Velocity going up means you spray to the to the ceiling, and there's a force that keep the particles suspend in the air. F capital B means buoyant, means floating force, and there's a drag on the object also. Okay, there's a drag on the object also. So in this case, you need to calculate the time. Need to time. Okay, U is moving downward. Weight velocity W, buoyant force is FB, drag is capital D. So the first equation we derive from the free body diagram is weight equal to drag plus Fv. Weight equal to drag plus Fv. Do you understand how you get this yellow colored equation? Raj, do you understand how you get W equal to D plus FB?
Yes, sir. So far,
Okay,
sir.
okay, good. So if this letter V is a particle volume, this is volume, or normally I will use this one, right? So in this case, I'll use a special symbol to represent the volume. So you should know how to calculate volume for a sphere, right? Okay. So you can calculate with to find the weight of the paint, itself on the molecule. What you take a specific weight times the volume. Specific weight times the volume, you'll get the weight. Okay. So how you convert the specific weight of the paint? You take Sg times what specific of the water times the volume of the sphere. Okay, so you need to convert into these two, convert into paint specific gravity. So how you convert? You take Sg times water specific weight times the volume of the sphere given by pi divided by 6 d cubed. Then how you find the buoyant force? Buoyant force given you by specific of the air times the volume of the sphere. So given you by this one, so you are given specific weight of the air times this one. You need to recall from your mathematics. Volume of the sphere equal to pi divided by 6 d cubed. So you have your W, you have your FB. So this one we derive already. So you have your FB, you have your weight. Now how you find your D? The problem next is how you find your D. D equal to standard equation. D equal to half rho V square A CD. So if you compare the above equation and the below one, half rho A, rho is the air, the medium that this particle went through. U is the velocity. A, how you calculate the air, the area. Area is what the velocity C. You imagine this one is your eye. The velocity is your eye. What do you see? You actually, if you look from below, the particles, you are seeing a circular body. Apologize for my drawing. It's not a perfect square, but you get the idea. You view from, imagine you are the velocity. Okay, so you view from the direction of the velocity. What do you see? You are seeing a sphere, a circle. So the area is pi d squared divided by 4, or you can use pi r squared, and then CD. So you get your D already. You combine these three, you rearrange, you're able to get the idea. So in this case, for simplification, we assume that our Reynolds number is less than 1. So we can use back the equation 24 divided by RE from the diagram itself. Just now I show you one diagram. For my slides, there is one graph, it is this one. Okay, so this graph only apply for Reynolds number less than 1. So let's say we assume our spray particles is sphere. So we are using CD equal to 24 divided by Reynolds number. Okay, so back to our case here. So you substitute your CD equal to 24 RE. Okay, then you convert what is the definition of Reynolds number. Reynolds number equal to rho VD divided by mu. Okay, so you substitute, and you rearrange the equation, you will get this form. You rearrange again the equation, you get 3 pi mu A UD. And then this is a substitution of all the equation that you have from the question. Reynolds number equal to rho VD divided by mu, rho 1.23, d 1 times 10 negative 5, velocity is 0.00365 meter per second, divided by dynamic viscosity 1.79 10 negative 5, you get this Reynolds number. Okay, then you solve, you'll get the velocity for, okay, these slides. Inside here, you can solve your d, u, d, then you can solve what is your u. Okay, so your u will be this number, okay, 0.003 meter per second. So you know that this velocity equal distance divided by time. So you just rearrange. So 8 foot is about 2.44 meter. 8 foot is about 2.44 meter. You know the velocity, you can calculate the time that it travel. Okay, distance you have, velocity you have, you're able to find. The time is about 668 seconds. So it's about 10 minutes plus. Okay, to fall to the ground, 2 meter. Okay, so it's quite direct for this example. Any question for this tutorial question? Any question?
No, sir.
Okay, good. All right, we go forward. Another one is compressibility effect, meaning how we know that we are looking at compressibility effect if your Mach number is more than 0.3, more than 0.3, then you're having a compressibility effect. So if you look at this diagram, this is from experiment diagram, CD versus Mach number, and I just put a line for you to observe. You have two different objects here. One is the ellipse shape, one is the square object. So if you increase your Mach number, so two questions you need to ask yourself from this graph. So what happened to the CD if your Mach number reduce? So if you can see for this object, the compressibility effect doesn't happen if it is below 0.5. As you can see, the CD quite constant. The CD value quite constant. However, for Mach number more than 0.5, as you can see, it keep increasing. More obvious for this object will be this region. Okay. Another one, it will be three different cross-section object. As you can see, the first one is a sharp pointed, second one is a sphere, third one is a cylinder. This one cylinder, circular cylinder. So you see CD versus Mach number. The highest one will be the circular cylinder as it spike out. As you increase the Mach number, CD will increase. However, for the sharp pointed, it will go up to a certain level, then it will drop. Okay, so this is also why you choose a certain shape in your design. Okay, so this is just some question to test you whether you understand or not. What happened at Mach number 1, what happened more than 1, and so on. So if you have a compressibility effect, you will see that the shock wave the shock wave, if you have Mach number 1, more than 1, you will see some phenomena called shock wave. So if you can see Mach number 1.5 and Mach number 3, you see that the shock wave will get near to the surface as you increase the Mach number. Okay, so the shock wave normally will happen like this, then it will be like that, then it will be like that. So you will near to the object itself. Let's say this is the object. Okay, then you will stick to the object. So for example, this one, right? This is just a schematic diagram, but you can see what happened if you increase the Mach number. The shock wave will getting near to the surface. Roughness of the surface, as you can see from the graph here, there's a chart here that you can refer if you want to find the surface roughness due to the friction. The small f is a friction. Okay. And this one is CD versus Reynolds number, also another important graph. As you can see, this you have a golf ball, and also there are some different ratio of the surface roughness to the diameter. Okay. So how do you use this graph? Okay, normally you calculate the Reynolds number, then you project up, you intersect with one of the point, and then you project to the left, like how you use the Moody diagram. Then you get your CD. After CD, you complete calculating the drag. So almost standard, okay, almost standard. So let's say you have a smooth surface and you calculate the Reynolds number, you get a Reynolds number, let's say you get this number, you project up, you intersect with the point, move to the left, you get one number. You use this number, CD number, to calculate the drag force. Okay, I'll show you one example. This is Moody diagram. I think you're familiar with it. There will be one question in the final exam that you need to use Moody diagram. Okay, let's go to this example. Okay, again, my favorite is on the round object, so pay attention to this example. So let's say you have a golf ball with a diameter 1.6 inch, and the weight is this one, can travel velocity at this speed, and a tennis ball with a diameter, weight, can travel at this speed. Ignore the unit, but I want you to focus on the steps itself, right? You can change it to unit SI if you want, but I want you to focus on the strategy of solving this kind of question. Right, determine the drag. The question asks you to determine the drag on the standard golf ball. So you have golf ball and you have tennis ball, right? So you have a few scenarios you need to solve. One standard golf ball, and then a smooth golf ball, and a table tennis cases at the condition given. Okay, so how do you solve this kind of question, and which graph that you should refer to? After you determine the drag, you need to calculate the deceleration of each ball for this condition. Deceleration means that A, okay, F equal to ma. So you need to calculate the A. F is what you calculate from the drag itself. Okay, drag is a force. Force equal to ma. So deceleration you calculate. Standard air kinematic viscosity given. This case kinematic viscosity given, and not dynamic viscosity, so don't confuse. Density of air is this one, and just to give you note now, if you compare this graph, this Reynolds number is given in kinematic viscosity. Take note, there's a different equation, but same value. One is in terms of kinematic viscosity, and Moody chart that you normally use, you can see you're using, this one is dynamic viscosity. Take note, Okay. dynamic viscosity. So in this tutorial question, we are using kinematic viscosity. Density air is given. So how do we find? First, drag equation, D equal to half rho U square A CD, or you can start with D equal to half rho V square, or U also can A and CD. Then you convert according to the problem statement here. So density is air is given. So your object is traveled in the air. So this density is the medium that you use, or the condition where the experiment conducting. So in this case, you're using air. So you're using density of air. Velocity depending on the speed itself. Area, again, area is what is seen from the velocity. U or V. Again, area always from where you see, from velocity. So you're having golf ball, no matter it's golf ball, smooth golf ball, table tennis, you're seeing a sphere, or you're seeing a circle for area. So you can use pi r square for area. CD, you need to find from the graph. Okay, need to find from the graph. So the first, the equation that you see, the question asks you to find drag. Expected answer from us is the drag equation. Okay, you can either write this one and then you modify a little bit to this one. So for golf ball in the air, you find the Reynolds number. Reynolds number equal to mu divided by kinematic viscosity. For golf ball, if you calculate the velocity of the golf ball, diameter, and kinematic viscosity is given. Okay, if you look back at the question, travel at this speed, right? Travel at this speed, you have the diameter, so you can calculate. Kinematic viscosity is given. Okay, so again, for this example, ignore the unit, just pay attention on the strategy, what we need to calculate. Okay, first, drag equation. Second, Reynolds number equation. You substitute the number, you get 1.79 for the golf ball. You do the same for tennis ball. You get another Reynolds number, 4.78. Okay, so you look back at the graph. So the first one, 1.79. So you go to the Reynolds number. Okay, Reynolds number here is UD divided by kinematic viscosity. So the first one, 1.8 10 power 5. 1.8 10 power 5. So this is 1. Okay, 1. This is 4. 1 to 4 divided by 2. This one is 2. 2 10 power 5. We have 1.8, right? Okay, we have, okay, our Reynolds number is 1.79. So it's about here. Okay, about 1.8. So we just draw a line on the graph. Then we have a golf ball, right? For golf ball, you're using this dot line. So intersect with this point. Move to the left. Here is about 2.5. So CD for normal golf ball is 2.5. Agree? Understand how you get 2.5? Cool, you okay? Cool, are you there?
Yeah.
Do you understand why you get 2.5?
Yes.
Okay, good. Right, stop me if you're not able to follow. First, we found the normal golf ball. Second, 1.79 for what? 1.79 for tennis ball. Sorry, for just now it's 1.79. Second one is 4 point. Second one is a smooth golf ball. So again, we use the same 1.79. First one is golf ball. Second one is a smooth golf ball. So the third one, we will use the same, but we look at smooth golf ball. We will follow this smooth line, solid line, smooth. You move to the left, you'll get about 5 point something. Okay, so CD for smooth golf ball is 5.1. For normal golf ball, CD is 0.25. Okay, agree? Just now we found what is happened to golf ball, normal one. And then for smooth surface, we will continue using the smooth line and intersect with the same Reynolds number for the tennis ball, for the golf ball. Then you move to the left, you get 5 point something. Then you do the same for a tennis ball, the Reynolds number 4 point something. So you go and find 4 point something, 10 power 4, somewhere here. Is it correct? Let me check. Okay, yeah, 10.4. Then 10 power 4. So you draw a line on the graph itself. Then we are using the smooth line. We get about 5. Okay, for tennis ball, we assume it's a smooth surface. So you get about 0.5. So you get 3 CD number. One is for normal golf ball, 0.25, smooth golf ball, 0.51, and for tennis ball is 0.5. So here we will have this 3 CD number, and then we solve for the drag depending on the CD number that we get from the graph. Okay. Density given, velocity given, diameter given, CD extract from graph already, you're able to find what is the drag. So if you substitute the number for golf ball, normal golf ball, you get this number. Smooth golf ball, you get this number. For tennis ball, you get this number. Okay, at this moment, ignore the unit, all right? But try to understand the procedure, okay, that we use. How do we use the chart? How do we use the drag equation? Okay, yeah. So because when it comes to a real scenario, all these parameters will be changing. So important is you know how to calculate the Reynolds number, how you apply this graph. Okay, how you apply this graph. All right. This is one of the example. So how we solve as the acceleration? So the acceleration, again, recall back the second Newton law or the Newton law, F equal to ma. So we know the weight equal to mg. So you rearrange the equation. You rearrange the second equation. You substitute back. You'll get F equal to W divided by G A. So you have a ratio between, then you rewrite again. You put the W over here. F divided by W equal to A divided by G. You get the ratio equation. So what does it mean? What does this equation mean to you? It means that the drag divided by weight of the object equal to acceleration divided by gravity. So for normal, you have 3 cases. If you take A divided by G is 1.86. How you get 1.86? You take the drag divided by weight itself. How you get drag? Drag you find just now. Okay, drag you find just now. These 3 value here. Okay, by using drag equation. How you find the weight? Let's look back at the question. Okay, the weight is given in the question. As you can see, the weight for golf ball equal to this one. Table tennis ball weight equal to this one. So the weight is given. So when you derive from the F equation, you put back, you found the drag, you have the W. So A over G is 1.86 for normal golf ball. Smooth golf ball A over G 3.86. Tennis ball is 4.77. So if you are given, you know the gravity value, right? 9.81. So acceleration for normal golf ball is 9.86 times 9.81 or G, or you can just put in the G form. For golf ball equal to 1.86 G, A for acceleration for smooth golf ball is 3.86 gravity. Tennis ball is A equal to 4.77 times 9.81 to get the acceleration. Okay. So this is how you get the acceleration, deceleration. The next one is, okay, I'm going to close this one with floor number. So this one you read through. Again, floor number is more on the wave. The keyword is wave. So you will not be covered in detail in this module. But however, if you go into work into the shipyard or any ship industry, maritime industry, then this floor number is important in your design. So these are the graph that used to calculate the CD versus floor number. You will no longer use Reynolds number, but use floor number if you're designing a ship. Composite body, okay, we'll cover this one later. Okay, composite body drag, there's one example about this one. Okay, let me stop here.